This video is a description of the double exponential smoothing model, and it's called the double exponential smoothing model because we're going to be smoothing out two things. We're going to be smoothing out our forecast for the time series itself, where we think the time series is located, but we're also going to be smoothing out our forecasts over time for how much the time series is going up or down. So if we go back to the previous sets of slides for exponential smoothing, and we just look at the equation for exponential smoothing, where yt hat for forecast, yt hat is the forecast for today. Alpha is the percent of the forecast that is dedicated to the immediate previous time period t minus 1. So t is the subscript for today. T minus 1 is the subscript for the last period, whatever that may be. It could be months, quarters, days, hours, weeks, minutes, you name it. I'm just going back to the immediate previous measurement in time that I had. So if you think of it as a ruler, you go back to the previous inch or the previous centimeter, or however refined your measurements on the ruler are. You're just going back one. And then 1 minus alpha is the remaining part of the forecast that's dedicated to everything else that we remember from the previous 2, 3, 4, 5, 6, 7 periods, whatever those are. So a large alpha, alpha close to 1, means that a bulk of the forecast is coming from the immediate preceding past, and our exponential smoothing forecast is going to look like the naive forecast. Not exactly, unless alpha is equal to 1. But if alpha is like 0.9, 0.95, 0.85, it's going to look a lot like the naive model. So the simple exponential smoothing is like, hey, a certain percent of your forecast is the previous data, like the naive, and the remaining component is the previous forecast, which incorporates everything else. The first forecast for the single exponential smoothing model is naive. So that is where we left off and discussed in the previous slides, but today I want to point out that the moving average, the exponential smoothing, the naive, the modified naive, all of these models have some nice properties if the time series is not trending up or down. So depending on what you want to do, you could use these models to make your forecast. However, if the time series is trending up or down, these models are going to have some significant problems, and we want to try to do something else. So if we think about what we mean by trend mean that the data are either consistently increasing or consistently decreasing. I use the word continually. I'd like to use the word consistently rather, just because we may see some periods where the trend is not as pronounced, or it goes down when it was going up for most of the time, but just for a little bit. So a nice example of this is US GDP, which has been going up for many, many consecutive quarters. Now it's going to go down in the next few quarters, but for the most part, GDP has been increasing over time. The S&P 500 has been increasing for the majority of the time since the 2008 housing market bubble. And if we were going to make predictions for where those time series were going, we would like to use some type of forecasting technique, but we would like to also think that maybe that technique should incorporate the fact that these time series have been going up. And so if we were to use the moving average, it's just relying on the past, and the past has been lower than where we think the time series will be tomorrow. If we use the naive, we have the same problem. If we use the exponential smoothing, we have the same problem. And if we consistently miss in the wrong direction, we have a biased forecast. So if I use any of these previous methods, I'm going to have a biased forecast if I'm predicting something that's going up or if I'm predicting something that's going down. So in either case, these models don't do very well. And so what we'd like to do is account for trends in the data. And let me just show you some of the problems that we could have if we don't. So why do we care about trend in the data? Why does it matter so much? Look, let's take a look at this table. Here I have a time series that everybody on planet Earth should be able to forecast, including my 3-year-old son. Maybe it's an exaggeration. Maybe 3, 4, 5-year-olds, maybe they shouldn't be able to forecast this. But everyone else probably has a good guess. Y is the data. It's located in the far left column. Y for period 1 is 2. Y for period 2 is 3. Y for period 3 is 4. Y for period 4 is 5, etc. So this is a deterministic data series in that the data goes up by 1 every single time. So if I'm making a forecast for period 8, that forecast should be 9. Absolutely should be 9. If you take a look at what Y8 should be, just have a look right here at the bottom left corner of the table. Y8 should be 9. What does the naive predict? 8. Let's see what we get if we do a 2-period moving average. So I can't make a forecast for period 1, that's out. I can't make a forecast for period 2, that's out. Then my forecast for period 3 is the average of 2 and 3, which is 2.5. So I should be predicting 4, and instead the prediction is 2.5. Well, let's see if we try the smoothing model. Maybe alpha equal 0.9. 0.9 times 3, that's the previous data point, is 2.7. 1 minus 0.9, which is 0.1, times 2 is 2.9. I missed by 1.1. So the naive is actually closer than both the moving average and the exponential smoothing. But I'm consistently missing by a factor of 1 or more every single time. And I don't catch up. Now, this should be an easy thing to forecast. I wouldn't think that I need a forecasting methodology in order to make this forecast. Yet here I am trying to adopt these methodologies and they don't work. That's an issue that we can resolve today, and we're going to resolve it with what's called the Holt double exponential smoothing model. So if the problem is that we don't have any trend in these forecasts, we are not being proactive about thinking of where the time series is going, even though it's very easy to see where it's going. Maybe we can try to put trend back into the forecast. And this would require us to know what the trend is, though. May not be the case. So in the previous example, we knew that the data were going up by 1 every time, but the data may not be going up by the same amount every time, or the amount that the data go up or down may change over time. So there may be some change in the pattern. So our goal here is to try to make a prediction for the data series. We need to accomplish 2 tasks. The first thing is to make a prediction for the level of the time series. So where do we think the time series is now? And then we need to make a prediction for where we think it's going. So based on the data, I'm going to evaluate where I think the time series is now. Based on the data and where the time series has been, I'm also going to try to evaluate where I think the time series is going. So when I make a forecast for the next period, I'm going to try to juice up the forecast, not just based on the level, which is what the naive, the moving average, and the single exponential smoothing models do, but I'm going to try to juice it up based on where I think it's going. So I'm going to try to explicitly incorporate some trend. And our forecast, we're going to have the level, which is what these methodologies on this slide 47 are talking about, the naive, the moving average, the exponential smoothing. Those are all level forecasts, but we're also going to throw in some trend. And so what do we have to do? We have to estimate the trend. Now we're going to do it with the Holt double exponential smoothing model. It's a little bit more complex in that not only are we trying to make a level prediction, but we're also trying to think a little bit carefully about where the time series is going. So there are 3 equations for the Holt double exponential smoothing model. And unlike the previous forecasting techniques where there's just been one equation, here we have an equation to make the forecast, which is what we've been doing, but then we have an equation that guides the level component of the forecast and an equation that guides the trend component. So when we make the forecast, it's being fed into by 2 other equations. So let's have a look at this first thing, the level equation. Level equation. LT hat is the level. Alpha is the percent of the level that is dedicated to the current data point. So once I obtain some data, once I observe the current period, I use that to make a current level. So I observe the data, then I make the level. The level consists of alpha times x, x is the data, plus 1 minus alpha times whatever the previous level was and whatever the previous trend was. So we make the level equation first. T xt minus 1 is our estimate for the trend in the previous period. Lt minus 1 is our estimate for the trend for the level in the previous period. We do the level first, then we do the trend next. Trend gamma is the smoothing parameter. So we think of the trend as being where the time series is going. So think of the level as being the flat part of the stair, and think of the trend as being the stair component, what's going up or what's going down. And so I'm estimating a staircase in a way. So T is the trend estimate for this period. It's where we think the time series is going. Gamma is the smoothing parameter. It's between 0 and 1. And we estimate where we think the time series is going based on our current level and our previous level. So we take the difference, and that's like a stair step. And then 1 minus gamma was our previous stair step multiplying t minus 1. So gamma is the smoothing parameter. We estimate a stair as the change in level. And then 1 minus gamma is the old trend. And we do this second. Why? Because if you take a look at the formula right here for the trend, the level that we found first goes into the trend. So you can't find the trend without finding the level. Then we make our forecast. Our forecast is for the next period. So it's xt plus 1. I take the level and I add m times the trend. M is how many periods in advance we try to make our forecast. Normally it's just one period. So I make my forecast based on adding the level and the trend. And so what we're doing is we're creating an average of both the level of the time series and the trend. They both change over time. Think about the amount of money that you have in savings over time. Obviously, there's a level at any given day that you check your balance. However, there's also a trend in your savings behavior. So if I'm trying to predict how much you'll have saved tomorrow, I might at least like to incorporate that there's some trend up or there's some trend down. And so we're getting an estimate of both the balance and kind of where it's going at the same time. To give you an example of maybe a non-time series, what this is doing, think of going down the stairs at night. It's very dark. You can't find the light, so you just go down blindly. You have an idea of where the next step is, but you can't see it, so your foot is trying to estimate that, and your foot goes down based on where the previous steps have been. So, the staircase may be a little bit uneven. Some steps may be smaller than other steps, but you make an estimate of how far down to step based on where you are now and where you've been. Okay, so lots to unpack here. The first thing we need to do to get started is to have an initial level and an initial trend. So we have the same type of problem that we had with the single exponential smoothing in that we don't know where to start. We get our initial level and trend by estimating a regression. We have the data as a function of just the period of time that we're in. So x is the data. Beta 0 is the slope, beta 0 is the intercept, that's the starting level. Beta 1 is the trend. So I estimate the data as a function of the time period. So basically what you do to get started is you fit a line through the first few data points, and the intercept is the initial level, and the slope is the initial trend. Okay. So let's take a look at how this model works. I have 6 periods of data. I fit a line through the first few data points, and I get an intercept of minus 0.47. So if I had a period 0, my estimate for what the data would be minus 0.47, and my estimate for the trend would be 1.6. All right, so L0 would be minus 0.47. T0 would be 1.606. All right, so let's put it into the level and trend equation. I get the minus 0.47 here and the 1.606 from fitting a regression through the data points. I'm going to have some smoothing parameters. Alpha is the smoothing parameter associated with the level. Gamma is the smoothing parameter associated with the trend. So the level equation, I have LT is equal to 0.8 times XT. X is the data, plus 1 minus 0.8 times old level plus old trend. So now let's look at this level column. 0.8 is the smoothing parameter. 1 is the data point for period 1. So my level for period 1, I have 80% of the level comes from the data point for period 1, which is 1. 20%, 1 minus 0.8, is multiplied times the old level, that was the minus 0.47, plus the old trend, which is the 1.606. So my estimate for the level in period 1 is 1.027. Now, I take that 1.027, that is the level for period 1, and it feeds into the trend equation. That's L1 minus L0 for period 1. I have 0.6 times 1.0272 minus a minus 0.47 plus 1 minus 0.6 times the old trend, which is 1.606. So I estimate the time series to go up 1.541 for the next period. Okay, that is my trend for period 1. Now when I go to period 2, I use the period 2 data for the level. And I have the previous level, which was L1, 1.027, plus the previous trend, which is T1, 1.541. And I get a new level of 2.754. That immediately goes into the trend equation. So I have 0.6, which is my smoothing parameter. My LT is for period 2, L2 minus LT minus 1, which is L1. L1 is the level for period 1 that we found, 1.027. And I just take the difference. Now the old trend was for T1, and that's 1.541. So I get a 1.652 as the trend for period 2. That feeds into period 3. So L3, I take the data for period 3, which is 4.5. I take the level for period 2, which we found, 2.754. I take the trend for period 2, which we found, 1.652. Plug them in, you get a new level. That level immediately feeds into the trend for period 3. 4.481 is the level for period 3 minus the level for period 2. And this was the trend for period 2. And we just keep iterating through. Now you might think this could be done in Excel, and you're right. These are the levels and trends for the previous periods. How do we make the forecast? So we make a forecast by adding the level and trend. The level for period 0 and the trend for period 0 we found from a regression. You add them, you get a forecast. Then the level for period 1 and the trend for period 1 come from the level and trend equations. You add them to get a forecast. So everything after the minus 0.47 in this column came out of the level equations, and everything after the 1.606 came out of the trend equations. This is the level and the trend. And we just keep adding throughout. Now Excel can do this for us. So I'm going to show you how to fit a line through the data with the double exponential smoothing model. And here I have the COVID cases for Carroll County from March 19th through yesterday, which is Friday the 10th. So I have about 21, 22 periods of data. We're going to start at period 0. There were no cases on the 19th. Okay, and I'm going to fill down. So I can fill down. These are the different periods that I have. Okay, so this is, let me just format these cells here. We don't see any decimals. There we go. All right, so I have period 0, no data. Period 1, first time I observed any data. Okay, how do I get the initial level and the initial trend? The initial level, I fit a line through the data points. Okay, so I'm going to insert a note here. This level comes from the regression. It's the intercept. And this comes from the regression. It's the slope. Now, let's go and use Excel to estimate a regression line through the first few data points. 3, 4, 5, doesn't really matter too much. Just use regression. Okay, so I'm going to use regression. X is the period. So we'll just go to the data and grab a few of these. Okay. And then Y is the data. Okay, and you can see that I have 5 data points, 3 through 7, 3 through 7. No labels, that's fine. Hit OK. All right, so 9.9 is the intercept that I get. And if we go back to the data, I'm going to put that right there, 9.9. 2.9 is the slope. I'm going to go back and put it right here. How do I make the forecast? It's the level plus trend. So I add the level and the trend. And let me just type that in here. Forecast is level plus trend. So as I make forecasts for these data, they're going to be the same all the way through. Now I'm going to use the level equation. Alpha, let's say the smoothing parameter for the level equation is 0.8. And the smoothing parameter for the trend equation, let's just set it equal to 0.5. We can always change it. Level equation. Alpha times the data. And this is the exact same methodology that you use for the single exponential smoothing. Plus 1 minus alpha times, really this is the forecast, but it's the old level plus the old trend. Old level plus the old trend. So I have alpha. Alpha is in I3. So it's I3 times the data, which is located in period or in column C. These are the COVID cases for Carroll County. And then I have 1 minus I3 times the old level plus the old trend. That's the level. Now the trend. Trend equation. I take gamma times the change in level. New level minus old level. Plus 1 minus gamma times the old trend. So I have gamma, that's in I4 times new level, which is in E3, minus the old level, which is in E2, plus 1 minus gamma times the old trend, which is in F2. 3.38. How do we interpret this? I should increase my estimate for the number of COVID cases in Carroll County by 3.38. Okay, and I can just copy these all the way down. And actually, I can make a forecast for today. My forecast would be 208 cases. Let's take a look at how this model does at predicting COVID cases in Carroll County. Let's just take a look at the error. We take the data. We take the data minus the forecast, and you can see the error over time. So the double exponential smoothing model did not predict the jump on the 25th very well, but it accounted for it quickly. It didn't predict the jump on the 30th very well, but it accounted for it very quickly, and it has accounted, for the most part, it has mirrored the data very well. we can see that actually, I think if we do a little bit of a graph here, we go to home, insert, let's just insert a 2D line. Okay, I'm going to delete that. Let's delete the graph actually. Maybe let me just put the number of cases and the forecast here. Let's see if we can do a two-dimensional line plot here. You can see that if you take a look at the orange and the blue, this is the data. That's the orange line. The blue is the forecast, and you can see that the double exponential smoothing model has forecasted these cases rather well. The blue line is pretty close to the orange line. Okay, and this is, we could clean up the graph a little bit if we wanted to. We could call it Carroll County COVID-19 predictions. And we can clean up the data a little bit too. We can give the data a name. I think I have the data in the forecast. Let's go back and select the data again. I think I flipped them here. But you can see that this is the type of modeling that if we just look at trying to match the time series, even though there's some nonlinearity in there, our forecast catches up quickly. It catches quickly. You can see the trend once we observe this 50 gets juiced up for the next period. So to summarize the double exponential smoothing model, how does it work? We have a level equation where we think the time series is to date. It incorporates the data. If we go back to Excel, here's the level equation. Note that it incorporates the data, the old level, and the old trend. The red is the data, the purple is the old level, the green is the old trend. Purple, let's take one more look. Red is the data, purple is the old level, green is the old trend. Then we have a trend equation. Red is the current level, purple is the old level, green is the old trend. Then we have a forecast. Level in blue, trend in red, 1 period ahead. What if I wanted to go multiple periods ahead? So this is for today. What if I wanted to forecast, this is for today. What if I wanted to forecast multiple periods ahead? No problem. You just take the level and add, this is 2 periods ahead, 2 times the trend. So basically, with the double exponential smoothing model, if I want to forecast a bunch of periods ahead, I take the most recent trend and then I make it into a straight line relationship. I will post more on the double exponential smoothing model on Courseden along with these slides. I'll have an example that we can work through. I understand the slides are not sufficient, nor is the video. However, I think after watching the video and the Excel tutorial, you can get kind of an idea of how this works, and then after looking at the handout, you'll have a better clue.